When we cross clock domains, we need a synchronizer. To understand why, let's talk a tiny bit about metastability. We will come back to metastability later in the course, but for now, if we have a flip-flop and our clock here, and if there's a rising edge of the clock, then remember our analogy that a flip-flop is going to take a photograph of what's on the D pin, and then a copy of that photograph will appear on the Q pin just after the rising edge. Now, by the same analogy, if you are moving when a photograph is taken, the photograph is going to be blurry. It's not going to be good. What actually can happen with an actual flip-flop is that the output, which is normally either a logic 0 or a logic 1, if we happen to take a photograph at exactly the wrong time because the input is changing, our flip-flop can somehow get stuck halfway between a digital 0 and a digital 1. So to be precise, every flip-flop has got supply rails. We don't normally show them, but there's a ground and there's a supply voltage. It might be 1.1 volts if it's inside our FPGA. It might be 5 volts if we're using traditional CMOS flip-flops. And a logic 1 is represented by the positive supply rail. A logic 0 is represented by ground. And so if our supply rail was 5 volts, then if our flip-flop becomes metastable, it will be stuck at 2.5 volts, which is halfway between 0 volts, which is a logic 0, and 5 volts, which is a logic 1. Although it is only an analogy, and you won't yet understand why, we will cover it later in the course, being stuck at this halfway point is analogous to having a very steep mountain here with 0 volts down here, 5 volts here, 2.5 volts right in the middle, and the flip-flop being stuck at 2.5 volts is like a ball balanced right at the top of these very steep slopes. It doesn't take much at all for this ball to either fall to the left or fall to the right, and once it starts to fall, it will quickly arrive at 0 or at 5 volts. This is due to the feedback mechanism within inside the flip-flop that will quickly drive it to either a 0 or a 5 volts. Noise is always present. There's always thermal noise. There's always other noise. These slopes are extremely steep because our flip-flops now are very fast, high speed. The feedback loops have got very high gain. So we are not going to stay stuck in the metastable state for long. In theory, we could stay stuck forever. In practice, within a nanosecond or so, we're going to fall out of the metastable state and return to either 0 or 1. Now, we have no way of predicting which way we will fall, but the key point is, quickly, if we do get stuck in a metastable state, then quite quickly, almost surely, we will exit the metastable state and be either a 0 or a 1. We may as well say we have 50% chance of going either way. When might we get stuck in a metastable state? Well, whenever the input is coming from an external source. The input might be a push button that a user pushes. A human being is not going to be synchronized to the clock in your FPGA, so a human could push the button at just the wrong moment and your flip-flop might become metastable. Alternatively, it might be another FPGA board communicating with your board. So on another FPGA board, it's got a finite state machine or flip-flops or whatever, and so on the other board, there's probably going to be a flip-flop, and then there's going to be some output logic here, and that might go to a pin on the FPGA, which you then connect up to the input of your FPGA here. And this clock and our clock for the white flip-flop are two different clocks. They're on two different boards. Even if they're both 50 megahertz, that's the nominal value. No clock is precisely 50 megahertz. In such situations then, we can never be sure that the output from this flip-flop won't change in such a way that by the time it goes through the combinational logic and into this one, it might well be that there's a rising edge here while this guy is still changing here. So this is what we talk about crossing clock domains. Whether it's a human pressing a button, whether it's another digital circuit communicating with ours, when they are not using the same clock, then there's always a danger that the input to our flip-flop here is going to change at the rising edge of a clock. This will knock this flip-flop into a metastable state, meaning it's stuck halfway between a logic 0 and a logic 1, and it's going to stay there for a short period of time. But if this is part of our finite state machine, and remember the output is our current state, if our current state is stuck halfway between 0 and 1, then who knows what the next state logic is going to do, and that's going to be fed around to the input of our flip-flop. And so if this problem isn't fixed up quickly, then our next input is going to be wrong. And also there's going to be some output logic here if this were a finite state machine, and so our actual output is going to be a nonsense while this guy is in a metastable state. So these things are not good. The way we solve them is by using 2 or more flip-flops in what's known as a synchronizer. We simply cascade flip-flops. And to understand why this works, we need to look at the timing diagram for them. So let's do that now. We have seen cascaded flip-flops before under the guise of shift registers. A synchronizer, and we could use just 2 or we could use 3. In the olden days, sometimes you did use 3 flip-flops. These days, the flip-flops are sufficiently high speed that often we just need 2, but in principle we can have more. Anyway, a synchronizer looks just like a shift register, except we're not going to read out the values at the intermediate stages. We simply care about the final output here. The analogy we have is that each flip-flop protects the previous ones from being in a metastable state. We'll explain why exactly, but in terms of an analogy, imagine that having the input change at the wrong time is like being hit with a ball, and the worse the timing, the harder the ball hits. So most of the time, this flip-flop is strong enough to absorb the ball coming here. Sometimes the ball might be coming hard enough to mess up this flip-flop here, but then the amount of energy left is sufficiently small that it does not upset this one. And if we've got 3 of them here, then you'd need an extremely high energy ball coming in to break this one, and break this one, and break the next one, and actually get through to cause trouble. So the more flip-flops we have, the greater the protection we have against an input changing at the wrong time. We can never fully guard against the input changing at the wrong time. That's a mathematical impossibility, at least according to classical mechanics. But we can reduce the probability of any harm being done to an extremely small probability. To explain this, we need a timing diagram. So I'm going to call this in, I'm going to call this, for lack of a better word, X, and I'm going to call this out. I've got in here, I've got X here, I've got out here, and most importantly, I need a clock. And my clock is going to be an ordinary clock. Okay. Provided the input does not change near the rising edge of the clock, then this will function exactly the same as a shift register, which we've looked at before. So I'm not going to really explain that case. Instead, I'm going to consider the interesting case when the input changes right at the rising edge of the clock and it knocks the first flip-flop into a metastable state. So let's have a look at what can happen then. Let's assume that initially X and out are both 0. My input's initially 0 and it transitions to a 1 right at the rising edge of a clock. If it's at just the wrong time, so to speak, then this flip-flop will enter a metastable state. That means that its output is going to be stuck halfway between a logic 0 and a logic 1. And so it's going to look something like this. Now the period that it gets stuck is random. Let's assume, though, that it gets unstuck about here. And it's different every time we run this, but it does become unstuck quite quickly. Now it can either go to a logic 1 or to a logic 0. We don't know. Let's, for argument's sake, draw both of them just in different colours. So let's draw in yellow the case it goes to a logic 0. So it drops down to 0 here, and then it stays 0 up until the next rising edge of the clock. What's the input doing? Well, synchronizers are not going to work, as we'll soon realise from timing diagrams, if the input changes too rapidly. So I need to assume that the input is constant for at least a few clock cycles if we have any chance for these guys to work. So let me assume that my input looks like this, and then for fun, let me have another transition down here, just to emphasize the point. So I get to repeat the exercise a second time. Okay, so my output X here, it's entered a metastable state because the input changed at the wrong time. After a random period of time it exits. The yellow trace assumes it exits to a logic 0. And being a flip-flop, the output's not going to change until there's a rising edge of the clock. Of course, if it's in a metastable state, there's the change to fall down or to fall up. But besides those two things, it won't change until the next rising edge. At the next rising edge, and here's the key point, because we have to assume that the input varies relatively slowly, at the next rising edge, the input is guaranteed to not be moving. And that's because it moved here, and it's not allowed to move too fast. So because it moved here, we know it's going to be constant for a while. And so then at this rising edge, we take a photograph of the clean input in. By the way, the assumption that the input is not varying too quickly is necessary even if we ignore metastability. If we are only sampling the input at the rising edge of the clock, if the input changes and changes back again between two rising edges, we're going to miss it completely. So regardless, we need our clock frequency to be significantly higher than the time in takes to toggle backwards and forwards, because otherwise we're going to miss what's happening. Anyway, back to our story. Our output X has gone metastable. It's balanced at the top of a very, very steep hill. Very soon it picks one way to roll, either to 0 or to 1. If it rolls to 0, it stays there until the next rising edge. At this next rising edge here, we see that we have got a clean input now in. And so therefore the flip-flop works normally. It photographs the input and it jumps up to a logic 1. And then it stays there all the way until up to the next rising edge. Had our flip-flop decided to go the other way, and it's entirely entitled to do so, then it would have exited the metastable state up here, and it would have stayed there until the next rising edge. At this rising edge here, the input is constant, and so it photographs the input. The input's a 1, so it stays a 1. So you see in both cases, and this is the key point, it doesn't matter which way it went, in both cases the output is eventually correct. So initially the output X is correct. A metastable event just means that there might be an extra clock cycle's delay before being correct, but it does end up correct. So the signal at X, besides this little bump here, is either going to be 0 then 1, or it's going to be 0 then 1 sooner. So in the yellow case, we detect the transition 1 clock cycle later. In the blue case, we detect the transition 1 clock cycle earlier. At worst, there's just a delay by 1 clock period. Nevertheless, we can't really directly use X because of this problem right up here. But if we now have a look at what this flip-flop is doing, we see that this flip-flop is not going to photograph any of this, because this flip-flop is going to photograph what happens at the rising edge, and going into a metastable state occurs just after the rising edge. Because remember, a flip-flop intentionally has an infinitesimal delay. The output does not change until just after the rising edge of the clock. So in other words, and what colour shall we use? If we use the red colour, the output at this rising edge of the clock, this flip-flop photographs X at the rising edge. X at the rising edge is still a 0. Only after the rising edge does it go metastable. So output stays 0 up until the next rising edge. And now we have a look. What's happening just before or just at the rising edge depends on which way the first flip-flop went. If the first flip-flop's a 0, then we're going to follow the 0 path until the next rising edge. And then at this next rising edge, if we're following the yellow path, we now go up to a 1. And we get this output here. If the first flip-flop had been following the blue path, then our output is going to, at this point, take a photograph of the blue curve and jump up 1 clock cycle earlier. And so the key observations are that the output is either going to detect the transition at in, either it will detect it 1 clock cycle later, or it will detect it 2 clock cycles later. But either way, it detects this transition, and that's all we care about, finding the transitions. Because we're sampling in, we're never going to know exactly when it changed. It might have changed here, or here, or here, or here. We'll never know that. And if it changes right at the rising edge of the clock, who's to say it changed just before, and who's to say it changed just after? To elaborate, let's assume that the input changed just before the rising edge, and there's no metastability, it changed sufficiently early. That means that this first flip-flop will photograph a 1 at the input at the rising edge here, so its output will be a 1. At the next rising edge, the second flip-flop will photograph this 1 coming out of the first flip-flop, and we will get the blue curve here. So we can say that this blue curve represents the case when the input changed just prior to the rising edge of the clock. Conversely, the yellow curve represents the same thing that would have happened had the input changed a bit after the rising edge. If the input changed after the rising edge and there's no metastability, X would remain 0 here and then jump up to a 1 here, causing the output flip-flop to jump up to 1, delayed by another clock cycle here. And so both are correct, because one person might have seen it occurred before and another person might have seen it occur later. So both these outputs are correct, whichever path we follow. And this is what we mean by the first flip-flop shielding the second flip-flop. The first flip-flop takes a hit, it's been knocked out for a while, but it gets up off the ground before the next rising edge of the clock, and therefore it presents to the next flip-flop a clean signal. And because the system's digital, whatever it presents, either a 0 or a 1, both of them are correct. A 0 is correct if we assume that the rising edge occurred just after, if we assume the transition of in occurred just after the rising edge of the clock. And the blue curve, a 1 picking a 1, well, that's correct had the input occurred just before the rising edge, and nobody can split the difference. Nobody's that accurate. Any two people watching will come up with a different answer, so both answers are correct. And this flip-flop, it gets back up off the ground and saves this flip-flop from photographing the metastable state. Now I won't actually do the same here, but we could. The story continues. It might then go metastable again, and we just follow the diagram through. Only in very exceptional cases will this first flip-flop enter a metastable state and stay there for a whole clock period. If it did that, then this second flip-flop is going to become metastable, because it's going to photograph, its input is going to be halfway between a logic 0 and a logic 1, so when this one photographs it, bad things can happen there. This flip-flop is going to exit from its metastable state with a certain probability over any period of time. And the key point is that this flip-flop will exit maybe 99.9999% of the time before the next clock cycle. And the same with this one. So the probability that both of them do not exit from a metastable state is going to be extremely, extremely, extremely low. And thereby these two are going to significantly shield a third flip-flop had we had one, which is why you keep adding flip-flops and you get an exponential decrease in the chance of anything going wrong, because the probability of even one of them being metastable for a long time is almost zero. The probability that two of them, and they're independent, that two of them exhibit that behavior is even less, and so forth, the more you have. With this diagram in mind, there's only one other thing to talk about, and that's what happens if we've got multiple bits coming in at once in a parallel format. We actually do not want to use synchronizers on each bit individually, because there's a danger there due to this variable delay here, and we'll discuss this next. Let's assume I have two bits of information coming in from some external device. And let's assume that together these two bits, which could either be 00, 01, 10, or 11, have got some meaning. They're a message for us. Maybe it's a missile system, so 00 might be idle, 01 might be active, 10 might be launch a missile, and 11 might be reset the system. And let's assume that the message that's going to be sent here is going to initially be idle, so both lines are 0, and then we want to reset the system, so we bring them both up to reset. Because they're coming from an external device, we're crossing clock domains, so we need to use synchronizers. But we've been warned not to use individual synchronizers on two or more wires, and we're going to see why. So let's assume that we did not heed the advice, and we're going to feed this into this double flip-flop synchronizer, and we're going to feed the other wire into this double flip-flop synchronizer here. And let's assume that our clock here and our clock here, it's the same clock. Let's assume that we have a rising edge at the clock just at the same time as these guys rise up here. Remember that depending on whether the metastable state resolves itself to a 0 or to a 1, these synchronizers are going to detect the transition here either one clock cycle earlier or one clock cycle later, depending on how the metastability resolved itself. And so in particular, the output might be that this double flip-flop synchronizer saw the transition earlier, while this one saw the transition one clock cycle later. And so what does this mean? This means that the output is, in this period here, the output here is going to be 0, 0. That means idle. That's good. During this period here, the output's going to be 1, 0. That means launch a missile. And that's pretty disastrous because we just wanted to reset our system, but we ended up launching a missile. Of course, at the next clock cycle, the output's going to be correct, 1, 1 reset, which is what was being sent, but we did manage to launch a missile when we didn't really want to do that. So we should never, unless there are extenuating circumstances, and we'll talk about that briefly, but in general, we should never put more than one wire through a double flip-flop synchronizer like this if the message being sent is arbitrary, because otherwise there are going to be periods when what we receive is not what was sent. It's okay to have a delay. It's okay if we're sending 00 to be delayed by 1 or 2 clock cycles before we then receive the new message 11. A delay is okay, but you notice that in here it's neither 00 nor 11. It's neither the old message nor the new message. We can get a spurious message if we try to use double flip-flop synchronizers on more than one wire here. So that's the danger. Don't do it. In this particular example, we can actually use a double flip-flop synchronizer if we agree to a certain protocol. So what we're going to do is that we are going to change these things around, and we're also going to assume that that the message is being sent. After we've sent one message, there are only 2 possible messages we can send next. So we're going to limit our ability. So what am I talking about? Let's assume that the messages we're going to send can be idle. If we're idle, then either we stay idle or we can go to reset. If we're in reset, then we can either go back to idle or we can go to active. And if we're in active, we can either go back to reset or forwards to launch. Now in this case, because I can either stay the same or move forwards or move backwards just 1 unit, we can use something known as a grey code to encode this. And the key thing about a grey code is that only 1 bit changes at a time. We got into trouble here because we changed 2 bits at once. We went from 00 to 11, and that's what got us into trouble. If we promise to only change 1 bit per clock cycle, in fact it needs to be a bit longer for safety measures, but if we promise to only change 1 bit per clock cycle, then we're not going to have this problem here of occurring. And the grey code does that for this. So idle, we can just give it 00. Reset, we can only change 1 bit at a time, so let's do 01. Active, we cannot call this one 10 because that would mean that both bits had to change. So I call active 11. And then for launch, I'm only allowed to change 1 bit and I need a unique code. And so the only thing I've got left that meets all those criteria is 10. So if we use this encoding to represent our messages, and if we promise to only change our message 1 step at a time, either by going forwards or backwards by 1 step, then we can get away with this scheme here. We can't go from 00 to 11 though, because that would mean that during this transition period here, which might occur, we might have received either a reset or a launch message by mistake.